Hi, welcome to Physics for Architects. So in today's introductory lecture, we're not going to cover anything that you need to remember. We'll cover these topics in more detail later. I want mainly today to give you a sense of what Physics for Architects is about. Our topics this semester, after a bit of review, will be waves, sound, light, heat, fluids, and electricity. And today we're going to use one key idea. That idea is ray tracing to model how wave fronts, so light and sound are both wave phenomena, so how wave fronts reflect from hard surfaces such as the surface of a mirror for light or the surfaces of this classroom, the hard surfaces of this classroom. And we're going to gain some insight through both seeing and hearing into why it is that an indoor space like this classroom sounds so different from an outdoor space like an open air field. And the key difference is going to be that the sound reaches you not only directly in an indoor space like this, but it also reflects off of the hard surfaces of the classroom. So again, welcome, and I hope today to give you sort of an overview of the different places where you'll see me throughout the semester. So you'll see me in this classroom, which is where we would normally teach this course, and you'll see me at home writing on a lightboard, and then we'll splice in other things as they seem to be useful for illustrating the key points. Okay. So, have you ever had a friend telephone you from a completely empty apartment? You know, no furniture, bare wood floors, and so on. So, this happens to me pretty often because my dad, as I was growing up, my dad was a framing contractor. He built wood frame houses. But nowadays, he's semi-retired, he works as a handyman, so sometimes he'll call me from a job site he's working on where somebody's remodeling a house, and, you know, of course, all the furniture and all the carpeting have been removed, so it's just a completely bare room, and I can tell from almost the instant when he says hello that he's on a job site, because his voice just sounds different. It has that I'm in an empty room with no furniture, no carpeting sound to it. And what is that sound? How is it that I'm able to tell? Now, you might not have heard that. You will in a moment. But something you probably have heard is if you've come and gone through 30th Street Station, taking the train in and out of Philadelphia, then, you know, maybe you've listened to the train announcements on the public address system at 30th Street Station. And if you've done that, you probably noticed that after the first couple of words are spoken, the sound is almost unintelligible. The successive words really blur together one into the other. So there's very poor speech intelligibility in that space of 30th Street Station. Again, why or what physical parameter expresses that? Or maybe here's another related difference. Think about the sound of a broadcast studio. If you imagine listening to a podcast recorded in a professional studio versus the sound of a classroom versus the sound of a concert hall designed for listening to music versus the sound of a cathedral designed for maybe choral music or chanting, something that changes at a very slow pace, or the notes are really sustained for a long time. These all sound very different. And you might have heard that recently in this era of the COVID-19 pandemic. If you listen to podcasts, a lot of us are accustomed to listening to our favorite podcasts recorded in a professional broadcast studio. And now some of those same people are recording their podcasts from their home offices or from their living rooms or their kitchens. And unless they have the resources to do a serious acoustic treatment of their home spaces, then probably the acoustical quality, you can tell probably that the sound has been recorded in a room that sounds very different. It's actually much more live sounding than a professional broadcast studio. So if you pause for just a moment and contemplate what is that key difference between a room that's acoustically live and a room that's acoustically dead. So I'm going to assume that there are a variety of contexts. You might be synchronous or asynchronous. So if you have somebody available, you could message or chat or talk to your neighbor about what they think. You could compare your answer with theirs. Or you could just think about it yourself. So I'm going to pause for just a moment. And the answer that comes to my mind is called reverberation time. Reverberation time. And what that means is if I make a sudden noise, like if I clap my hands, then the question is, how long does that sound persist? Or, now I'm not a good singer, but if I were to hum a note or play a note with a musical instrument, like, then from the moment when I stop, the question is, how long does that sound persist? So if we had, like, say, let's just be imprecise and say loudness versus time, then maybe I'm humming, and then I stop humming. So maybe in a relatively dead space, maybe something like this happens, and maybe in a more acoustically live space, something like this happens, so it takes a lot longer to decay away. And actually, it often turns out that in spaces where the sound takes longer to decay away, actually the steady level is even higher, because especially if you're humming a constant note, because the sound actually can build up over a longer time and fill the space for a longer time. So you actually end up with a higher sound level if you're in a more reverberant room. Okay, so we're going to hear that in just a minute with an example. But here's another thing to think about, or if you have a neighbor available, you can discuss it with your neighbor, which is, what kind of space sounds more live or more reverberant? How about a large versus a small space? So do you expect a larger reverberation time in a large space versus a small space? And I guess for that you can think about a classroom versus a cathedral maybe. And then also, how about like hard versus soft surfaces? Surface treatments or surfaces? Surface treatments, how about that? So in other words, do we have carpeting on the floor? Do we have plush curtains? Do we have lots of plush furniture? Or do we have something like hard plaster walls, hard wood floors, or concrete floors, and so on. So then if you think, well, would I expect a more live sound, a longer reverberation time in a large room or in a small room? And would I expect a more live sound, a longer reverberation time in a room with hard surfaces versus a room with soft surfaces? And if you keep that in your mind for a moment, then we're going to address some of that with a few sound samples that we're going to clip in right after this.
Regional, Wilmington, Baltimore, EWI in Carrollton, Washington, stairway number 5.
I'm in the reverberation chamber at the University of Edinburgh. Here the walls and the ceiling are all hard plastered to give maximum sound reflection. When I speak to you, what you're hearing is the direct sound from my mouth, together with multiple reflections from the walls, the ceiling and the floor. I've come through now to the anechoic chamber. Anechoic means non-echoing. The walls, the ceiling and even the floor in this chamber are lined with foam wedges which absorb the sound. So the room's almost free from reflections. When I'm speaking, all you're hearing is the direct sound from my mouth. You can hear the sound is much clearer than in the reverberation chamber next door. But correspondingly, the overall sound level is much less.
The field of architectural acoustics was born in the year 1895 when a young assistant professor of physics named Wallace Sabine was assigned the actually thought to be impossible. He was assigned this task not really thinking that he would succeed in completing it. Was assigned the task by his department chair of improving the acoustics in the just recently constructed Fogg Lecture Hall on the Harvard University campus. So the Fogg Lecture Hall no longer exists, but it's now the site of the Fogg Art Museum on the Harvard campus. So when this lecture hall, it was designed as a classroom, so it was kind of a medium-sized classroom lecture hall, sort of like, comparable to DRL A1 on the Penn campus, if you've been in that room. And when it was first built, the reverberation time was sort of comparable to the reverberation time that you heard in that sample of 30th Street Station, maybe even a little worse than that, kind of like a reverberation time from a big cathedral. It was maybe 3-4 seconds reverberation time. And that made the spoken words of a lecture, you can see how hard it is to understand the words of the train announcer at 30th Street Station. So imagine something a little bit worse than that, and imagine somebody trying to read more quickly and communicate something technically challenging like an academic lecture. So it made the room basically useless for its intended purpose because the speech intelligibility was extremely poor. So Sabine he set about the task of trying to improve this. So he basically worked in the quietest hours of the night. So he waited till after midnight, maybe between midnight and 5 in the morning, when the Boston area streetcars were not running. And he measured the reverberation time. He did that by, say, clapping his hands and then measuring with a stopwatch how long it took before the sound of the clap was no longer at all audible, before it became imperceptibly quiet. Or, maybe he would use some kind of a musical instrument to sound a tone and then stop and measure with his stopwatch how long it took for the sound to decay away. And maybe each individual measurement wasn't too precise, but he could statistically gather up many, many measurements and accumulate an average that way. And then, what's he able to vary? So he went across the street to the to Sanders Theater, which is the biggest auditorium on the Harvard campus, so it's kind of analogous to the Irvine Auditorium on our Penn campus. And he borrowed the seat cushions. So the seat cushions were probably a little smaller than a meter by a little smaller than a meter in cross-section, in area. And he took these borrowed seat cushions and he put a varying number of them up along the surfaces, let's say along the surfaces, the outside wall of the lecture hall. And now some places, some locations turn out to be more effective than others. It often turns out that the corners are the place to start because the corners are one of the more effective places to absorb the sound. But in any case, he varied the number of these seat cushions that he put along the walls of the lecture hall, and made careful measurements of what the effect was of varying the fraction of the surface area of the lecture hall that was covered in seat cushions. And I guess two important things resulted. One is that he actually made this auditorium useful. so it actually became usable. I think it wasn't actually that long before this lecture hall was torn down and rebuilt. But in any case, at least over the next several years, he made the room usable acoustically. And he also worked out a result which is not, it doesn't appear in very many ordinary physics courses, but it's actually extremely well known in the field of architectural acoustics. He worked out this result known to this day as Sabine's formula, which is that the reverberation time, and this was derived for a rectangular room, so the result works best for a rectangular room, reverberation time. So the reverberation time and often this is called RT60 for reasons that we'll get into much later when we really study sound for real. Now we're just giving you kind of a preview of what the course is about. But the 60 refers to 60 decibels. So in other words, the sound level, you might have heard, if you look at the volume level on a audio equipment, sometimes it's measured in decibels. So 60 decibels down from its peak levels. The reverberation time is, there's some numerical constant, which works out to be about 55, and then times the room volume, which you could measure in cubic meters or in cubic feet. And then there's the speed of sound, which you can measure in meters per second or in feet per second. So the speed of sound is about 343 meters per second, which is about 1,100 feet per second. And then times the absorbing area. And the absorbing area is, just measured in square meters or square feet. So it's just area, but it's not exactly area. It's area weighted by how absorptive it is. So this absorbing area is, we could use the Greek symbol sigma for adding things up. So that's like all of the, here, let's say we take the room. Suppose we take the room and we chop the surface up into little squares like this, and we'll say this is 1, 2, 3, 4, 5, 6, 7, 8. So each one of these things is a square meter. Then we're going to, so here's I is 1, 2, 3, 4, et cetera, et cetera. So we'll take the area I and then times the absorption. This is a lot of detail. You don't have to know any of this today. I'm just giving you a preview. So that means, okay, so that would be kind of like A1 absorption coefficient 1 plus A2 absorption coefficient 2 plus A3 absorption coefficient 3, And this absorption coefficient is, say, 0 for a hard surface, or not exactly 0, but pretty close, small number, hard surface. And it's 1 for an open window. And then it'd be a pretty big number, like say 0.8 or 0.9 for one of those nice seat cushions stolen from Sanders Theater, borrowed. So, the more, so you go add up all of the surface area of the room, and it basically counts for nothing if it's a hard surface like hard plaster or concrete or hardwood floor, but it counts, with a big fraction of the area if it has a nice layer of soft plush material on it. So the reverberation time has the volume of the room upstairs. These are just constants. It has the volume of the room upstairs, and then it has how much area is covered with good absorber downstairs. So if you take a bigger room, like 30th Street Station, for a given type of surface, that's going to have a longer reverberation time. I think that makes intuitive sense. You imagine hearing the reverberation of your voice in a very large room versus a small room. Makes sense that the large room reverberates for longer. And then if you take the same size room, and we're going to see that in an example in just a second, then if you cover more and more of the area with really good absorption. So you can see this sometimes in loud restaurants if they want to improve the speech intelligibility of the restaurant, if they want to get it so that you can talk to the person across the table from you without too much background noise. They'll put absorptive tiles on the ceilings. Carpeting isn't always great in restaurants, but you can, sometimes you can use carpeting, or you can put some kind of soft material on the walls. The easiest place to put it is the ceiling, of course, because aesthetically and functionally it works best on the ceiling. But in any case, you cover as much of the surface area of the room as is feasible with a really good absorber, and you can cut the reverberation time down. So then if you went in when there's nobody there, you could do this reverberation test. Or if you go in when there are a lot of people there, the fact that each person's voice reverberates for less time means that the overall sound level is lower when you have many people talking, and you can more easily hear just the sound of the person across from you at the table. Actually, after solving this seemingly impossible problem, Sabine had now developed a pretty good reputation and a lot of knowledge in the field of architectural acoustics. So he went on to actually design the acoustics of the Boston Symphony Hall, which is actually known as quite a nice symphony hall. Yeah. So, and this is I think it's a shoebox style. It's kind of a shoebox style concert hall. But in any case, he basically designed the acoustical performance of that hall before it was built, and the results were outstanding. So, and actually there's sort of a long history of architectural acoustics in the Boston area with, especially there's a group out of MIT, and there's actually a consulting firm that my colleague Richard Farley works with called Ascendtech. So they're in the Boston area, and they're actually related to, they kind of are an outgrowth of one of the famous architectural acoustics experts from the Massachusetts Institute of Technology from MIT. So there's actually quite a bit of architectural acoustics brain power still in the Boston area. So Sabine, he solved this problem that he was assigned by his department chair. He came up with this formula, which is still useful for quick estimates to this day, although people use computer models for really detailed estimates. And he designed the acoustics for the Boston Symphony Hall. Okay, so now let's listen. What we're going to do in the next clip is we will listen to the same room, but with a sequence of different absorption treatments. So you'll hear that. So Physics 8 and Physics 9 are both known as Physics for Architects. So Physics 8 is Physics for Architects Part 1. Physics 9 is Physics for Architects Part 2. So it's a two-part college physics course that we teach in alternate fall semesters. So Physics 8 in 2019, Physics 9 in 2020, Physics 8 in 2021, Physics 9 in 2022 is our current plan. Now, as I said earlier, you don't have to take Part 1 before you take Part 2. You can take just Part 2, or you can take just Part 1, or you can take Part 2 first and then Part 1. That's perfectly fine. But if you're taking Part 2, Physics 9, before or without taking Part 1, then I'm going to assume that you had a pretty good high school physics course, so that some of these topics, so the Physics 8 topics that we cover, you don't have to know all of these, but the Physics 8 topics that we cover, Physics 8 basically discusses Newton's laws of motion. And so we talk about time, position, velocity, acceleration, momentum, energy, power, force, torque. And actually, once you know force and torque, you can start to think about analyzing architectural structures. And then we finally wrap up Physics 8 with a discussion of vibration and oscillation. So Physics 8 is much more closely related to the architectural structures aspect of your architecture education, whereas Physics 9 is going to turn out to be much more closely related to kind of the environmental systems side of architecture. So in Physics 9, we first do some review, since I'm going to assume that you might not have seen classical mechanics, Newton's laws of motion, maybe since high school, or maybe Physics 8 was a year or more ago. So we'll do a little bit of review of the physics that I want you to have seen before, and then we'll go on to talking about waves, and then sound, and then light. And by the way, sound and light are both wave phenomena. So we do waves in general, and then sound is a really nice example of that, and light is a nice example of that. And then fluids, and then heat, and then electricity. So that's kind of the list of topics. Those are the main topics for Physics 9. So we're going to assume, coming in here, and we'll do a little review, we're going to assume that you're basically familiar with, let's say, velocity, acceleration, force, energy, power, and so on. And we'll remind you. So we try to emphasize in this course the topics that are most relevant for architecture majors, and we try as best we can to connect the physics in the course to examples drawn from architecture. And my friend and colleague Richard Farley, who has been teaching architectural structures, that's Arch 435 or Arch 535, at Penn in the design school for decades, and he was a student of the famous architect Louis Kahn. He sat in on every class meeting for this course for the past several years, just about, and he's going to help keep us honest. So he'll bring in some examples of his own of how these physics topics apply to architecture from time to time. So we try to make the course fun, interesting, and stress-free. You're going to read, so I want you to read before class so that what we talk about in class is fresh in your mind. So you're going to read, oh, that's very bright. You're going to read, you're going to watch some asynchronous lectures like this one. We're going to solve some homework problems together in synchronous sessions. So I think that's, sometimes we'll spend a synchronous time talking together or reviewing things, but I think most of the time what we'll do, aside from answering questions or some review, we'll basically work together in small groups on solving the week's homework problems in the synchronous sessions. And then each week, after you've completed, so again, most of the homework problems you will complete during the, you'll have a chance to complete during the synchronous time, so you won't really have to spend much time at all at home working on these things. But you will turn in on Canvas a PDF scan of your own solutions to the week's homework problems. And then also, each time you read something, I know when I was in college, if a professor asked me to read something, it was pretty rare that I actually did it on time. So, but I really want you to read so that if you come to class having already read, then if something doesn't make sense to you, you know that you did the reading, you feel confident asking a question. So, and we're kind of all on the same page when we come to class. And we can make good use of the time we spend together. So each reading assignment, and I might do this for the asynchronous lectures, we'll see. I'm kind of, we're trying something new here. Each reading assignment will come with questions that you're going to answer on a web form, and then I can read your response to the reading. And something you'll probably find surprising is that a good fraction of the time I will actually respond to your response to the reading so that we can kind of have a conversation back and forth about what you're reading. But we don't have midterm exams. We don't have quizzes. There's no curve, so I have there's no limit, no fixed limit on how many people can earn an A. It's just a fixed cutoff for, I say 90% or higher is at least an A minus. If you get 100% or higher, you can get an A plus. To get 100%, you have to do well on everything, and you also probably have to do a little bit of extra credit work. There are many different extra credit options. And then if you get 80% or better, then you get at least a straight B. And then I don't want to be more specific than that, but that's a pretty good guideline. We also don't have labs, although there might be a couple of kind of optional extra credit lab-like things you can do if you want to. So if you took Physics 8 last fall, or if you plan to take Physics 8 next fall, Physics 8 has an emphasis more on forces, torque, vectors, and so on. That's the stuff you need for the structures side of architecture. So our studying waves, sound, light, fluids, heat, and electricity this semester will be most relevant to the environmental systems side of architecture. Another common theme will be basically transforming energy from one form to another. So to some degree, there is some discussion of sustainable design or what you have to do to convert. For example, you might wonder, how does a power station convert fossil fuels into electricity? Or how does an electric motor convert electricity into mechanical motion? Or you might say, gee, maybe I have a solar farm and I'm collecting sunlight, and maybe I'm collecting at peak more energy, more power than I need. Let's say more energy per unit time than I need. What can I do with that extra energy? Well, maybe you can pump a fluid like water up a hill, and then at night you can release that fluid back down and get back some gravitational potential energy to do some load leveling. So, and then we'll see how incident light or how incident sunlight, say, can heat a building or heat the surface of a building. And we can see how that varies with, say, the angle of the surface with respect to the incoming sunlight. So we'll see things related to transformation of energy, related to sustainable design. It also often turns out that some of the things that you have to do to make a building more energy efficient have the side effect of improving its acoustical comfort. So it's kind of interesting that these things connect to each other in some way, in that thicker windows or double layer windows or better insulated walls often improve the acoustical separation between spaces. Sometimes more energy efficient air conditioning systems or heating systems the motors run at a lower power and they're quieter, they're kind of inherently quieter. So sometimes it turns out that environmental comfort has a nice side effect of acoustical comfort. So we think that architecture students will find these topics relevant, especially with today's emphasis on sustainable design. If you're not an architecture student, then we hope you'll find Physics 9 to be a fun, interesting, and really quite stress-free way to satisfy the college's physical world sector requirement. Okay, I guess I'm saying this for like the fourth time now. So you're welcome to take Physics 9 without having first taken Physics 8. Or you can take Physics 9 first, and then next year you can take Physics 8. If you didn't take Physics 8, we're going to assume that you took, say, honors high school physics, or at least a pretty good high school physics course. So you're familiar with how to use Newton's laws of motion, kind of the basic ideas of time, position, velocity, acceleration. The idea that energy is 1/2 mv squared, where v is velocity or speed, is pretty important. Some of the stuff like force and torque isn't going to come up very often this semester. This stuff doesn't really come up too often this semester, but I just want to kind of assume a common background. And then energy in particular is a it'll be a recurring theme. But anyway, if these topics from Physics 8 feel a bit rusty, don't worry about that, because we're going to begin with some review. Okay, now another question to discuss with your neighbor, if you have a neighbor, or you can text somebody to discuss, or you can just wait and ponder it for a moment. But which of the following contains more energy? A, 1 gram of chocolate chip cookies, or B, 1 gram of TNT. That's basically dynamite, the explosive trinitrotoluene. So you can think about that for a moment. There's no reason you should know the answer. So this will be a topic that you will read about. You'll read Richard Muller's very interesting, chatty discussion of this topic, full of interesting anecdotes, when you read Chapter 1 of Physics and Technology for Future Presidents, which is the reading you're going to do by the weekend. So you'd say, well, TNT is an explosive. It must contain a huge amount of energy. Chocolate chip cookies are a snack. Why would a snack contain a huge amount of energy? But it actually turns out, as Richard Muller will tell you, and I guess we'll briefly look at a table in a moment, that a gram of chocolate chip cookies contains more energy than a gram of TNT. And you say, well, if that's true, then why would you use TNT to, let's say, do mining, to blow a hole in a mountain? Why wouldn't you use chocolate chip cookies? Well, you could use chocolate chip cookies if you use the chocolate chip cookies to feed a bunch of college students with hammers and picks, and then they put that energy into, digging up the mountain. Although you then have to factor in the efficiency of human muscles. But it turns out that even though TNT releases less energy per gram than chocolate chip cookies do, the TNT releases that energy much faster. So the energy per unit time is bigger, or the power of the explosion is bigger. And one reason for that Professor Muller explains, and Richard Muller is a UC Berkeley physics professor, and he's actually had a really interesting career, but I digress. So the TNT does not need oxygen to burn, whereas the chocolate chip cookies are combined with oxygen. So the fact that the TNT basically, for the chocolate chip cookies to burn, you need to add oxygen and heat. For the TNT to burn, you only need to add heat. You don't need to add oxygen. So that allows this chemical reaction to proceed more quickly than this one, as you'll see in Richard Muller's chapter. And then this idea that you take some kind of food, like chocolate chip cookies, let's say they're some combination of sugar and fat, and you combine them with oxygen to metabolize them. So you know that to burn a typical fuel, you need fuel, oxygen, and heat. So you're going to see right after I erase this board here, you're going to see me do a kind of fun demonstration in the DRL auditorium of the physics department of combusting some kind of a food material. Okay, so the answer turns out to be a gram of chocolate chip cookies has more energy than a gram of TNT, which is quite surprising. But this energy comes out faster, that's why it's so useful. A related question is how much energy is released when you burn or metabolize 1 gram of chocolate chip cookies. So if you do a lot of like wilderness backpacking, or if you're kind of a survivalist, or if you're, you might know this. I learned a lot of these numbers at some point when I was trying to, one of my friends and I were trying to do a 2-week wilderness backpacking trip. We had to carry everything with us we needed to survive for 2 weeks. So we were really looking for, we're trying to figure out, how do different foods compare in number of calories per gram. So the most convenient units to use here are dietary calories. So in chemistry, calorie with a little c is 4.18 joules. But when you're talking about dietary calories, we usually use a capital C. So a calorie with a capital C is 4,180 joules, or about 4,000 joules. And actually, I think if you buy a can of soda pop, Coca-Cola, let's say, in Europe or most places outside the United States, I think the label on the back actually says either kilocalories or kilojoules, whereas in the US it just says calories. So they're talking about chemistry calories. Anyway, so a calorie, which chemists would call a kilocalorie, is 4,180 joules. So it turns out that pure fat, and I know this from backpacking, pure fats would be like olive oil or butter or something like that. Pure fat is, I think, something like 9 calories. No, oops, big C. So let me make a big C here. 9 calories per gram. And I think a lot of carbohydrates, spaghetti, stuff like that, are more like 4. And then I think if you take like chocolate, if you get like bars of chocolate, it turns out to be, sugar or chocolate, I think. Chocolate or sugar. I'm doing this from memory, but I think it's kind of something more like 6 calories per gram. And then I think, a lot of things like spaghetti, are maybe more like 4 or 5 calories per gram. So I don't know, somewhat interesting numbers. Okay, so we're going to go to the next little clip. You're going to see an experiment, and we'll go on from there. All right. So we know that a lot of food products are combustible. Richard Muller is going to tell you about chocolate chip cookies being combustible. But here's some generic coffee creamer that if you don't have milk around, you can use to lighten your coffee. And this stuff is largely sugar, so you can burn it. And to burn something like this, you need fuel. This will be our fuel. You're going to need oxygen. We've got the oxygen. And you need some kind of a heat source. In this case, our heat source is going to be the flame coming out of this blowtorch. So let's take some of this coffee creamer, and we're just going to pour it into this funnel so that when I blow on this end, it's going to take a nice kind of diffuse ball of coffee creamer and spread it out into the air to make it a nice flame effect. So I've got, I'm kind of filling up, about a third of the tube with coffee creamer. And now let's do so that's our fuel. We've got our oxygen. Now our heat source is this blowtorch. Look at that, blowtorch. I don't want to torch the camera, but you can see fire. And so here we go. Are you ready? Pretty decent. For the end of this week, you're going to read the first chapter. The title of the chapter is Energy, of Richard Muller's Physics and Technology for Future Presidents. It doesn't have very many equations in it, but it has lots of really kind of neat anecdotes that will bring the physics to life for you. So you'll see this table. The numbers are kind of rounded off, but he's talking about energy, and this first column is dietary calories for 1 gram of whatever substance. So at the top of the list here is a gram of material moving at the speed of sound. So let's say a few hundred meters per second, 1,000 feet per second. And that's only 0.01 dietary calories per gram. And you can go down a little bit from there, and we see some reversible forms of chemical storage, batteries. And then we're up, about a factor of 10 above the gram of speed of sound projectile. Okay, then here's TNT checking in at 0.65, which you can compare with chocolate chip cookies. So it seems like there's
almost a factor of 10, actually, between TNT and chocolate chip cookies per gram. That's kind of surprising, but again, Muller will explain to you that the energy comes out much faster in TNT. So then you have chemical fuels, including food, that you burn irreversibly, whereas with a battery, usually you can do things reversibly. And okay, so now we have like several calories per gram. You list butter up here at 7. I'm pretty sure I remember olive oil being 9. Okay, then a little bit above butter or olive oil is gasoline at 10, and then natural gas that you would heat your house with at 13 calories per gram. And then even about a factor of 2 beyond that is hydrogen gas. So if you use electricity to separate water into hydrogen and oxygen, and then you just carry around the hydrogen as a transportation fuel, then per unit weight, hydrogen is actually about 2.5 times as good as gasoline. Gasoline's more convenient because it takes up a lower volume. It turns out to carry the hydrogen around, you have to store it in some compressed form, and it's going to take up a fair amount of space. But still, it seems as if hydrogen has potentially a very promising future as a transportation fuel. And so there's talk about using solar farms to produce hydrogen gas, which you then use as a fuel. So then you can produce fuel when you have an abundance of sunshine, and you can consume it later. There's also talk of instead of going directly to hydrogen, you can say produce with solar cells some kind of alcohol. So then that would be a little bit more in the gasoline range. It's a little bit more convenient in liquid form rather than compressed gas form. Okay, then this kind of strikingly large number is a projectile moving at, see, this 30 kilometers per second is basically the speed at which Earth moves around the sun. So the asteroid that killed off the dinosaurs 65 million years ago, of course, it was much, much larger than a gram. It was actually comparable in density to Earth as a whole, and it was about 10 kilometers in diameter. And it was moving at about the speed at which Earth moves in its orbit around the sun. So then you can see that 1 gram moving, because you know the 1/2 mv squared, if you remember that from your first physics course. So you get this velocity squared. So 30 kilometers per second squared versus 1,000 feet per second, or say 300 meters per second squared. So here's 100 versus 0.01. So that is a factor of 10 to the 4th, right? A factor of 10,000 more energy per gram for something moving at Earth orbital speed versus moving at speed of sound. And then way, way off the charts here at the bottom of this table is if you're able to harness the energy stored in an atomic nucleus, you know, say with a fission reaction by splitting up uranium atoms, nuclei, then now you've got, you know, say 10 million, what's that? That's 10 to the 7th versus 10 to the 2. So that's like a factor of 100,000 more energy per gram than even this, you know, quite large asteroid number. So when you go through Richard Muller's chapter on energy, do pause to look at this table. It's sort of remarkable just how, well, first of all, you can get a sense for some of the everyday numbers, and then you can just see just how amazingly widely these various ways of, you know, potentially storing energy vary in order of magnitude.
So energy will be a recurring topic this semester as we make our way through waves, sound, light, fluids, heat, and electricity. So speaking of light, which we will cover in detail around the end of this month, what does adding a mirror do to a small space? You know, so here, if I just have a dark wall here and I look at the wall, all I see is the wall. But if I have a mirror here, then it sort of looks as if it looks as if there's actually space on the other side of the mirror. Of course, that's just a reflection of the space over here, but it looks as if there's something over here. So if I am standing here and I see my reflection in the mirror, where does my reflection appear to be? I guess my reflection appears to be on the other side of the mirror. That's why it makes the space look bigger. It looks like there's something over here. Now, do I appear to be right directly here? Or maybe way, way over here? I think it'll turn out that I appear to be as far away from the mirror on this side as I am on this side. So if I'm actually, let's say, 2 meters away from the mirror, then my reflection will appear to be 4 meters away from me, or 2 meters away from the mirror on the other side. So it'll be something like this, challenging my drawing abilities here. Oh, and then, okay, let's see if we can work out how that works. So here's a mirrored surface. Let's suppose this green surface here is a mirrored surface. Then here's an incoming light ray. And the way we work this out is we say, let's imagine this line called the surface normal. So this dashed line is perpendicular to the surface of the mirror, and the incoming ray, its angle with respect to the surface normal will be the same as the angle of the reflected ray with respect to the surface normal, as we'll see when we study light. So this angle is the same as this angle. So then if we do something like that over here, let's look at a few rays that reach my eye. So, well, here's an easy one. Let's see what happens. I look directly at myself, and that's not too interesting because I just see the ray bounce back with 0 angle in, 0 angle out. But then if I continue that ray all the way across, well, okay, I drew it a little bit, not quite right, but you can see it reaches the eye of my reflection. And then what about my big toe over here? So now if the angle in and the angle out will be the same, then I think I split the difference here to get the geometry right. So I'll come up like this, and then I'll go like that. So there's a ray of light going that way. And then if I were to continue that line, it should meet the big toe of my reflection. Okay, I didn't draw it quite right, but that's the idea. Or we could say the middle of me. So here's the middle of me. And we can do something like this. And then again, what does my eye see? I think we're really running into the limitation of my drawing skills. But, okay, we see something that's kind of plausibly the middle of me. So, you know, your brain doesn't realize that the rays are bouncing. So your brain sees something that's just coming, it thinks that the rays are going straight. But in fact, they're bouncing with this angle with respect to the surface normal. This angle is the same as this angle, or this angle is the same as this angle, and these angles are both 0. So you see what looks like a reflection of you as far away on that side as you are on this side. So you're kind of accustomed to the idea that adding a mirror to a space makes the space look a little bit bigger, because if we reveal the mirror here, then you see something when you look here that is not, well, let's suppose this was up against the wall, then, you know, it looks as if there's something else. And where does that something else appear to be? That something else appears to be behind the wall. It appears to be behind the mirror. So it looks as if space back here, which might be completely empty. I mean, there might be, who knows? You don't know what's really back here. But it looks as if that space that you can't see is occupied by what in fact is over here. And in fact, if you look at a flat mirror, then you see the camera is you see the camera appearing to be behind the mirror. And then you could ask, well, how far behind the mirror does the camera appear to you to be? And if, let's say, it looks as if you, the camera, are about 2 meters away from me right now. So in fact, it should look to you as if the camera is about 4 meters away from you. So the image that you see of the camera appears to be as far behind the mirror as the actual camera is in front of the mirror. So if you were going to tell the camera to autofocus on itself, if it's actually 2 meters away from the mirror, then it should autofocus for a distance of 4 meters. So actually we call this a virtual image, what you see here, because the place that the rays of light appear to be coming from is not where they're actually coming from. There actually could be something entirely different going on in this area behind the mirror. But what you think you see behind the mirror is a camera. You can also see here, while we're here, let me show you the auditorium that we wish we were able to teach to you in under different circumstances. So normally, this is the biggest auditorium in the David Rittenhouse lab. We normally wouldn't offer this course in quite such a big auditorium, but there's another one next door that's about half this size that we normally would offer this course in. So let's see what we can do with the fact that I'm over here and you see an image of me who appears to be on the opposite side of the mirror. And in fact, if I am a little less than a meter away from the mirror, then you see a copy of me who appears to be about 2 meters away from me, a little less than 2 meters. And you know, if I come over here, if I put my left hand here, then you see something that appears to be a right hand about as far behind the mirror as my left hand is in front of the mirror. So what's really going on back here, of course, you don't see, but you know, you see something that appears to be back there. What can we do with that? Well, it creates an excuse for kind of a neat optical illusion. So here's my left leg, and you also see what appears to be a right leg. Of course, right now I'm sitting on the top of the mirror, so if I don't do that, if I maybe straddle it just like this, so now, you know, it looks like both my legs, it looks as if both of my feet are up in the air. If I could do this, you know, indefinitely, then I might actually be a pretty decent basketball player. So when we cover the topic of light optics about a month from now, you'll see that a lot of what we do to demonstrate light involves smoke and mirrors. So I've got the Discotech smoke machine here and a laser. And let's see if we can see what the laser beam does when it reflects off of the mirror. So here's the mirrored surface. And I think if we get just the right amount of smoke, then you should be able to see that the outgoing beam of light, the reflected beam of light, makes the same angle with respect to the flat mirror as the incoming beam of light does. So the outgoing ray emerges at the same angle with respect to the surface normal as the ingoing ray. That's pretty good. That's very good. So we saw for a flat mirror, we have the angle of incidence and the angle of reflection and we draw this hypothetical, the surface normal, the imaginary line, the hypothetical line perpendicular to the surface, and this angle with respect to the surface normal is the same as this angle with respect to the surface angle. Well, what happens if the mirror is not flat? What if it's a curved surface like this? Well, at any given point along the surface, we can draw the surface normal. So here the surface normal looks like this. Here the surface normal looks like this. Here the surface normal looks like this. And then at that point, we say, okay, here's the incoming ray with respect to the surface normal. And so that angle is going to be the same as the angle of the outgoing ray, the reflected ray, with respect to the surface normal. We can do that wherever the light happens to hit the mirrored surface. So then if we take, let's suppose our mirror is part of a sphere. So if you do a cross section, it's like the arc of a circle. Then if we have a bunch of parallel lines coming in, then here is the surface normal over here, and we'll get a reflection like this. A ray that comes in right on the equator will just go directly back the way it came from. A ray from down here will go up here. Let's say a ray from over here will go up here. And we'll see that all of these incoming parallel rays actually focus to a point. So we call this distance the focal length. And it'll turn out, we'll see in about a month from now, that this focal length is half of the radius of curvature of this circle. So if you were going to trace out this circle with a piece of string and a tack, so you know what the radius is, then this focal length is actually half of that radius it works out to be. So we're going to see that also with a laser light bouncing off a mirror in just a moment. So this kind of mirror, it's a concave mirror. Yeah, this is a concave mirror. It's a focusing mirror. This is the kind of mirror that you would use to get a close-up view of your face if you're shaving or if you're putting on makeup. And it's different. You know, there's a different kind of mirror that you would use so you can kind of see a wide-angle view when you're driving or if you're like a shopkeeper monitoring a store. Okay, the next mirror we're going to look at is a concave mirror. So this is a mirror that will focus parallel beams of light. We'll see that in just a second. But this might be familiar to you. I remember when I was a little kid, I was fascinated by my mother's makeup mirror. So this is the sort of mirror that you would use up close to get a close-up of your face if you're shaving or if you're applying makeup. And I was fascinated by my mother's makeup mirror because if I held it really close, or if I stood really close to it, I would see a magnified version of my own face. But then what I really enjoy doing is backing away from it. And as you get to just the right distance, then suddenly you no longer see a magnified version of yourself, you see an upside down version of yourself. And I never understood why that was true. So later, when we talk about light in some detail, we'll see in detail why that's true. You can see the upside down picture of the camera now, and it's not magnified. If we get a little closer, you will see a right side up image of the camera that is magnified. Okay, so we won't worry about why that works today. It may just be a familiar fact from childhood. And let's see what happens when we bounce light off of this mirror. And I'm going to try. Let's take the discotheque smoke machine again. And yeah. Okay, so at every point along the mirror, the angle of reflection equals the angle of incidence, but the angle of the mirrored surface itself, so the angle of the surface normal. So here's the surface normal, and the surface normal goes like that. So the surface normal will change as we go from point to point along the mirror. and therefore the direction of the reflected beam will change. And then this is more dramatic if you take several parallel beams. Let me see if we can do that. But here are many parallel beams of light. Oh, I'm going to turn off the auditorium lights. This may be even a little more obvious. So you can't see the parallel rays going in, although if I see, you can see the parallel rays this way. But you can see the rays come out and focus to a point on the pink background.
You can see the same effect if you do a web search for London walkie-talkie building. You can see that somebody, probably somebody who didn't take physics for architects, designed this very kind of aesthetically appealing concave surface for the facade of this building in London. And you can see that what it does to the sun, you can kind of imagine what it does to the sun. What it does to the sun is kind of similar if you ever used a magnifying glass to burn things with sunlight. So at just the right time of year and just the right time of day, the sun's rays come in, and the sun's rays are basically parallel when they arrive. They get focused by this curved building facade, and they wind up concentrating quite a bit of solar energy on a little spot on the ground here. So looking up at that spot on the building, it looks extremely bright, much brighter than the sun. Or, well, this is kind of an exaggeration, but this effect has actually done damage to cars. Okay, maybe the building isn't really giving you this evil smile, and maybe the car isn't really being picked up off the ground like that. But here is actually a melted mirror, or part of a driver's side door. Well, actually, probably in London, it's a passenger side door on the side of a car. So you can see, damage from concentrating the sun's rays onto a small point, because the facade of that building was, in effect, a focusing mirror. So here's an example of, by learning a bit of physics, if you're going to design something that lives in the physical world, you kind of keep in the back of your mind what questions to ask. Here's one more example of damage done to that car by concentrated rays of the sun. So, you can maybe imagine that physics for architects is relevant for architecture. So if you want to find this, you can do a web search for London walkie-talkie building melts cars.
So this same mirror-like principle that we saw working with light rays actually can also be used to model the propagation of sound. So we can use ray tracing to model, essentially, like sound really travels out in waves, but we can pretend that the wave fronts are little rays going out perpendicular to the wave fronts, as we'll see several weeks from now. So, and this works especially well for higher frequency sound, where the wavelength is small compared to the size of any kind of surface that the sound waves might bounce off of. So if we imagine a person singing on a stage, and then these little red wave fronts would be kind of the sound waves emanating from the person's mouth, then you often see up above, in front of a stage, up a little bit higher, you often see a sort of angled, flat reflector. And when it's angled like this, then you'll see a sound ray bounce from this point at this angle and maybe head toward these seats, and another sound ray bounce up here at this angle and head toward these seats, and another sound ray bounce at this angle and head maybe toward the back seats. And so that's pretty good because it spreads out, it diffuses the sound, spreads the sound, the reflected sound. Everybody gets the direct sound, but then in addition, there's the reflected sound reaching the audience. This is not what you typically want in a listening space. So this is a concave surface, and as we saw with the concave mirror and the light rays, this tends to focus the outgoing rays of sound coming from the singer into, so then all of the sound will be concentrated, all the reflected sound will be concentrated near these seats close by. That's kind of a hot spot. And then there's a cold spot over here where you get no reflected sound. So this is definitely undesirable for an auditorium for listening to music. You get lots of reflected sound over here, no reflected sound over here. This is usually what you're aiming for. Sometimes you want to aim for something even a little bit more like this. So it's kind of a curved, a convex surface up above and up above the stage, just in front of it. And then you'll see it spreads out the sound even more widely between the front of the auditorium and the back of the auditorium. So it turns out that for a good listening experience in a space designed for listening to music or performance, you want to feel as if you're enveloped, kind of surrounded by the sound coming at you from several directions. And you want to feel as if that sound is arriving at about the same time. So next time you're listening to a performance, sitting in a performance space, kind of listen with your ear at the directions as you hear the music, and then also imagine with your mind's eye the sound, the kind of rays of sound going from the orchestra, maybe bouncing off that reflector up above the stage, maybe bouncing off of the right wall, bouncing off of the left wall, and then see if you can kind of hear that. And if the direct sound and the reflected sound all reach your brain or your ears, say within about 30 milliseconds, that's kind of 30 one-thousandths of a second, which means that since sound travels at 1,100 feet per second, about 1,000 feet per second, then you want the difference in path lengths between the direct sound and the sound reflecting from this side, the sound reflecting from this side, the sound reflecting off of that reflector up above the stage. So you want those different path lengths to differ by no more than about 30 feet or about 10 meters so that your brain perceives it as just a full sound all arriving at the same time. If the sound differences are much larger than about 30 milliseconds, then it'll sound more like a reflection, like an echo. Yeah, it'll sound more like an echo to your brain, and that's a less pleasant experience. So this is definitely something that people consider when designing acoustical spaces, and then once you have this kind of idea in your mind, you can look around, and next time you're listening to music, kind of imagine the different directions that the sound is reflecting and approaching you from. If you feel that the sound is, if you only feel that the sound is in front of you, versus maybe if you're in a really good seat in the orchestra section, then you feel that the sound is actually reaching you from several different directions and enveloping you. So now here's a more visual way of imagining Sabine's formula. So imagine here I am, and I'm sharing a space with a very noisy machine. And these are two copies of the same scenario, except in this case, I have a plaster ceiling, plaster wall, tile floor. So not only do I get the direct sound from the machine, the sound bounces off the floor and it comes toward me without really being attenuated at all. The sound bounces off the wall behind me, it comes back at me without really being attenuated at all. The sound bounces around the room this way, the sound bounces off the ceiling and it comes toward me without really being attenuated at all. And then, by comparison, suppose I have sound absorbing panels on the walls. Suppose I have some nice plush carpeting down here. Suppose I have sound absorbing ceiling tiles, maybe suspended from the ceiling. Then the same sound rays emanate out from the noisy machine, but every time they bounce, they lose a good fraction of the energy that they're carrying. So this ray will bounce off the ceiling, and I drew it as a kind of a dashed line to indicate that it's still going in that direction, but with a much smaller energy, or we say sound intensity. And here this one even bounces twice, so it's much, much reduced in intensity or energy. And over here, here's a ray that hits the wall behind me, but again, when it reflects with a much slower energy level than it. So the direct ray still reaches me with the same sound intensity, but all of the rays that reflect off of these properly treated surfaces, the carpeted floor, the wall with the sound absorbing panels, the ceiling with the sound absorbing ceiling tiles, every time one of these rays reflects from one of those surfaces, it's significantly attenuated. And so now we can get some idea again for going back to Sabine's formula, which said that the reverberation time is proportional to the room volume, and inversely proportional to the absorbing surface, right? It's the absorbing area. So if this is like meters cubed divided by meters squared, then you say the reverberation time is proportionally, oh, and then downstairs there's also the speed of sound. Speed of sound. So the speed of sound lets us, speed of sound downstairs converts meters into seconds. So you'll say, okay, if the sound travels a longer distance between bounces, then it's going to take a longer time to attenuate. It's going to reverberate for a longer time. That sort of makes sense. If you made the room bigger, the sound would travel for a bigger distance, and therefore, because of the speed of sound, a bigger time between bounces. So it would take a longer time for the sound to dissipate. That gives you a longer reverberation time. And then meanwhile, every time the sound bounces, it gets attenuated if it bounces from a surface which is treated. If it bounces from a hard surface, it doesn't get attenuated. So you can see it makes sense that the reverberation time is longer. The sound lasts for longer in the room if it bounces off of hard surfaces. The sound decays away more quickly if it bounces off of these attenuating sort of soft treated surfaces. And as a result, here what reaches me is the direct sound plus a much, much attenuated version, a highly attenuated version of the reflected sound. Here what reaches me is the direct sound plus basically the full strength of the reflected sound. So the sound level from this noisy machine that reaches me is going to be much larger here. The sound level that reaches me will be considerably smaller here because any sound that reaches me after reflecting will be significantly attenuated in, let's just say, energy. In the energy carried by each of these sound rays will be significantly attenuated each time it bounces. So here's a noisy machine. I want to coexist with it. It might be a restaurant, and these are the noisy other people in the restaurant, and I want to talk just to the person right next to me. And so, okay, you can't do anything about the direct sound coming from the people who are at the table across the aisle, but you can do something about the sound that reflects off the ceiling, the sound that reflects off the wall, the sound that reflects off the floor. So then that is reduced, and then you're only hearing the sound coming directly from the person sitting across from you, plus a highly attenuated copy of the sound that comes from, the people several tables away that you really don't want to listen to. So soft or porous surfaces absorb sound in a kind of way that's analogous to a dark surface absorbing light. And a hard surface reflects sound sort of in a way that's analogous to a mirror reflecting light. So once we get this idea of ray tracing, then that lets us kind of visualize in our mind's eye, and you can even model this on a computer if you have a geometry in mind. Then you can imagine the reflecting paths, just as you would imagine reflecting paths for light, and you can treat the different surfaces to reduce reflections, or you can sculpt the angles of the different surfaces to redirect the reflections, depending on whether you're talking about a space that you want to enjoy with minimal background noise versus a space that you want to use to listen to a performance.
So now that we've seen the idea of using ray tracing both to model light and to model sound, I want to show you just a quick clip from a piece of software called ODEON that is used to model the acoustics of a space that's being designed. So you can take your CAD model of a space that you are designing, and then you can essentially model what that space will sound like. This isn't something you're going to have to learn to do. One or two people in the past have checked it out for extra credit, but I think it's something to be aware of so that, again, one of the purposes of physics for architects is to make you aware of what technical questions to ask that can affect how something you design exists in the physical world.
It's watertight, so that rays are not escaping through holes in the geometry, and it seems fair that this is a fairly watertight geometry. And what you can also use it for is to verify that you haven't put your source below the floor or inside a column or a box or whatever, so that you have a valid source position, so it can easily be seen that this works. Another visualization tool we have is the 3D billiard, and it plays with a number of billiard balls and shows you how they reflect in the walls of the room and how sounds get scattered by surfaces depending on the size of the surfaces and the material types and so on. Quite a neat visualization, and you can also look in different directions in the room, so having a vertical radiation of these billiard balls or into the 3D space as well. So this is the 3D billiard display, quite easy to use. Last tab I want to show is the BRIA. It's the binaural room impulse response. And the binaural room impulse response is what you get if you go into a room, clap your hands and then record it at some other receiver location, what happens at the left ear and the right ear of a receiver at a dummy head or a living person with microphones in each of the ears. And then you might get something like this, left ear, right ear. And by using this as a filter to a process we call audition, you can listen to how will sound at this receiver position when the source is playing some signal. And listening through this through headphones, then you'll get a kind of 3D experience which is very realistic. Let's try to do that. So we can press this streaming convolution button and listen to some signal.
The Athenian agora and the South Slope. It was during the 5th century before Christ that the Athenian agora began to take shape as the commercial and civic center of Athens.
And we can also listen to
About the middle of that
sound,
century, the center
so
of
the dry
public
recording.
theater activities was moved from its temporary the Athenian agora and the South Slope. It was during the 5th century before Christ that the Athenian agora
or indeed to some other signal, or listen to it in another receiver position if we have calculated such one.
So another thing we'll see toward the end of this month is that light likes to follow the path of least time. And the path that results from that depends on how quickly light can travel in different media. So, for example, light travels faster in air than it does in water, and it travels even more slowly in glass than it does in water. And you can sort of see that by analogy with the fact that suppose you want to go from point A to point B, maybe you're on a walk through the woods, and maybe this is dry land, and then you have to cross a river, and here's some more dry land. So if you want to take the path that gets you there the most quickly, you notice that you can walk much more quickly on land. When you cross into the river, you're going to walk much more slowly. Now, if it were much more slowly, you would go perpendicular to the shore when you cross the water. But let's say you go more slowly in the river than you do on land, but not by a gigantic factor. So if you're trying to cross at an angle like this, then you will turn toward the slower medium so that your path in the slower medium is shortened a little bit, and then you'll turn back toward that original direction. And by making these two turns, you have optimized, you've minimized the total time that it takes you. If you were going perpendicular, then you would just keep going straight. But if you're already going at an angle, then you change your direction so that the distance that you travel through the slow medium is a little shorter, and then you go back. And so you want to, spend a little bit more distance in the fast medium, a little bit less distance in the slow medium. And we can see that in the demonstration with the laser and the glass block. But when you see something like that, when you see this thing called refraction, which is how light or a wave changes direction when it changes medium, you can think, by analogy with what would I do if I were at a boundary between land and water. And you change your angle such that you don't have to travel quite so far in the slower water. You travel a little farther on the faster land. And this turns out to tell you the principle by which a lens works. So you say, how do I know how the different rays of light bend so that a lens does its focusing job? We'll see that when we study light. And you can understand that by understanding that light takes the path of least time when it goes from a medium with one speed to a medium with another speed. And then usually the denser the medium, the slower the propagation speed of light in that medium. A similar thing happens with sound, and actually Richard Muller has some good stories to tell you about that also in his Physics and Technology for Future Presidents. So, for example, about which weather conditions let you hear faraway sounds versus which ones don't. We'll get to that in a week or two. So we've been talking about light rays reflecting off of mirrored surfaces. Here's just a little digression. This is called not reflection but refraction. It's what light does when it encounters a change in medium, a medium in which the speed of light is different on one side of a boundary from the other. So here's air, here's glass, here's air again. And you can kind of imagine that you are walking through the woods, and then maybe you encounter some knee-deep water. If you're just going in a straight line, your trajectory doesn't change. But if you were going, say, diagonally like this, then you would change direction a little bit when you first encounter the water, because you want to spend a little bit less distance in the water. Light takes the path of least time. And then you'll bend your direction back. So you can see that by bending a little bit toward the glass as we enter the glass, and then bending back away from the glass as we leave the glass, we, in effect, are minimizing the total time that the light takes, because we travel a little bit, the light travels more slowly in the glass than it does in the air. And so this is more pronounced if we make the angle as different from perpendicular to the shoreline as possible. So that's pretty good. So there you can see that the light bends sort of toward the glass when it enters, and then it bends back away from the glass when it exits. So the outgoing ray on the far side is parallel to the incoming ray, but there are two changes of angle in between. So you can also see a little bit of a reflected ray because the surface reflects a little bit of the incoming beam. So for the reflected ray, the reflected light beam is the same angle as the incoming light beam with respect to the surface normal. But then you can see that there's a change in angle for the transmitted beam, which we call the refracted beam. So you can also see a little bit of a reflected ray because the surface reflects a little bit of the incoming beam. So for the reflected ray, the reflected light beam is the same angle as the incoming light beam with respect to the surface normal. But then you can see that there's a change in angle for the transmitted beam, which we call the refracted beam.